Okay, we're going to do some security of routing protocols, OSPF and EIGRP. We're going to explore a routing configuration with our three routers. You can see our router in the middle is an area border router between OSPF and EIGRP. And we can see that we have routes being injected into each domain, EIGRP into OSPF and vice versa. We're going to look at some tools here, specifically in Kali Linux, that we're going to attack these routers, and then we'll put in some countermeasures for OSPF and EIGRP on router 2, so we'll double click on that. First, we'll do a show run, and we're going to pipe that to the router section. So there's EIGRP process 10 on network 10/8. We're redistributing into OSPF. There's OSPF 100, redistributing into EIGRP, and process 10 with the subnets keyword. So both routing protocols have all the interfaces in the 10/8 network, and both protocols are redistributing routes into the other protocol domain. Let's do a show IP route. As you can see here, router 1 is aware of all the subnets in the topology. Take a look at that again. Notice the networks here, 10.10.1.0, and then 10.10.2.0, then 10.10.3.0. And down there we have our management VLAN with a WinPC and a Kali PC. Also, router 1 is only running OSPF. 10.10.2/24 is the standard OSPF. And then notice the OE2 code. There's our external OSPF route that's being redistributed from EIGRP into OSPF process 100 by router number 2. Let's do a show IP route on router 3. Router 3 also knows about all the subnets from the topology diagram. It's only running EIGRP. Notice the D code, D as in the dual algorithm for EIGRP. The standard route is 10.10.2/24. And then we can see our external route above that, that is distributed from OSPF. Now we're going to look at Loki on Kali Linux, which is an exploit tool that we can use to cause problems in our routed network. Loki's written in Python, and the source code's pretty easy to understand. It's easy to customize and make your own. And you can make your own attack tools with Ruby or Python or whatever you want to use and customize that. That's what makes these exploit kits so powerful. Loki is a little bit buggy, but it's much more effective with OSPF than EIGRP. So let's go over to the Kali PC, open up a shell, and launch Loki. Okay, so loki.py Python. We're going to click on these little gears, this little gear button, looking for Ethernet 0. That's all we have on this virtual environment. Click on OK. Click on the routing tab, and we're looking for OSPF. We see two hosts, 10.10.10.1 and 10.10.10.2. This is router 1 and router 2. We're also going to see other data like the area 0. Also, there's no authentication yet. Okay, nothing used. Let's start the hello process. We'll set the authentication type to auth none and click on hello. See our OSPF states, two-way, XStart, loading, full. Okay, that's how we end the process. We'll expand the 10.2 router. We can see the link states that Loki has received from router 2. This is the great information in a reconnaissance attack. We can extract the fact that it's a poorly secured environment and other information about these routers. Now we can also actually inject illegitimate routes into the routing tables. We can cause routing loops and black holes. This is a denial of service attack. We can also use this to redirect traffic as a man-in-the-middle attack, steal information, maybe get system access by hijacking connections. So let's go ahead and inject a 32-bit mask route into the OSPF network and redirect traffic destined for 10.10.3.20 to our Kali PC here. As a matter of fact, we'll also notice that this route will be redistributed or propagated into the EIGRP network through the redistribution on router 2. So it's even going to affect the routing tables on router 3, which has a direct connection to that network. So it's crazy. Click on the injection tab. Network is 10.10.3.20 with a 32-bit mask. Make sure the type is type router links and click on the add button. Now let's go to router 1 and check out the routing table. Notice that entry, this OSPF 10.10.3.20/32 via 10.10.10.60, that's our poisoned injected route. On router 3, we'll do a show IP route. We'll also notice here DEX 10.10.3.20/32 via 10.10.10.2. Because of redistribution, it doesn't know that the Kali PC is the actual next hop that's known by router 2. Now, even though router 3 is directly connected to the 10.10.10.3, it's going to prefer this /32 route. Okay? It doesn't care if it's an external route or even that it was injected maliciously using Loki. It's going to choose that particular prefix. Now let's use trace route. Check this out. To 10.10.3.20. We'll verify that router 3 is actually using 10.10.10.2 as the next hop when it tries to reach 3.20. Do a Control-Shift-6 and stop that. Now the trace is failing at the second hop because the IP header is not changing as the packet's moving from router to router. So router 2 is forwarding the packet destined to 10.10.3.20 to the Kali PC MAC address. That's the rogue in our situation. And the Kali PC is not configured to receive packets for anything other than its own IP address, 10.10.10.60. So it's just silently dropping those packets. Now it's very important to use a hashed message authentication code to provide integrity and origin authentication for these updates and these packets sent between these routing neighbors. Now, this is not confidentiality, okay? It's not encrypted, but the attacker can't get the key, the secret or private key, will have protection of integrity and origin authentication using an HMAC. Let's go back to router 1, global configuration mode, and we're going to create a keychain. And we create these keychains typically to create a key management system or a group of keys that would have lifetimes, they can overlap each other's, kind of a key management system, a manual system. So we're going to call this keychain OSP. Let's do OSPF keys, dash keys. This is just a basic example here. Now we're configuring the keychain. We're going to call this key 1. Not a very good example of a key. It should be way stronger, but key string keys. The weakest, lamest password next to Cisco we could possibly have. How about KEY? We'll make it even more basic. So don't do this in the real world. So what are we going to use for our algorithm here? Notice our options: HMAC SHA-1, SHA-256, 384, SHA-512, and MD5. We really want to avoid SHA-1 and MD5. We'd like to use the SHA-2 family with this SHA-256, SHA-384, and SHA-512. Now I'm just going to use MD5 for this basic lab example, but in the real world, obviously, 256 or higher. Okay, I'm showing the keychain. There's key 1, and you can see the text is key. And notice it has an accept lifetime and a send lifetime, and that's how you could set up these lifetimes for key 1, key 2, key 3, key 4, and so on. And they could overlap each other, and this would be your kind of administrative manual key management that you could do on this router. So they could be, valid for 45 to 60 days to 90 days or whatever. And the first key could overlap, let's say a week of key 2. That's a good way to do it in the real world, but we're going to keep it simple. Let's do a show IP OSPF neighbors. So we have a defined keychain, but it hasn't been applied because router 2 in the Kali PC, our rogue router at 10.10.60, they're actually OSPF neighbors, as we can see here. So let's apply the keychains to gigabit 01 on router 1, interface gigabit 01, IP OSPF, authentication or authn, that'll do it, key-chain, and we call this OSPF-keys. Probably want to use all capital letters, but I didn't. Now, at this point, router 1 is not going to accept any messages on gigabit 01 because it doesn't have the proper MD5 information with the key string. Now, neither router 2 or the Kali PC have this key. So soon here, we'll start to see hello timers timing out. We'll see the neighbor relationship being torn down, syslog messages showing. And again, as you can see here, I'm kind of, stalling for time. There we go. Full to down, dead timer expired, dead timer expired. So neighbor down. So let's go to router 2 and repeat this configuration, and we'll actually change the name of the key chain, which is locally significant, but we'll use the same definition for key 1. So let's see what happens here. On router 2, you can also see that we've gone to a down state. So let's do configure terminal, and we'll say key chain, and the key chain name is going to be router-keys because it's locally significant. It doesn't matter to the other routers. And we're going to use the same key string, KEY. That's important. And we're going to use the same primitive, which is cryptographic-algorithm. We're going to use MD5. And again, this is not a real-world implementation, just a lab environment. On gigabit 01, we want to do IP OSPF authenticate or authentication, key-chain, and then it's, of course, called router-keys. And we'll start to see, there we go, loading to full, loading done. So we're back up to our OSPF neighborship very quickly. We've reestablished our neighbor relationship between router 1 and router 2. And again, the key chain names don't have to match, but the key values do. So key 1 and the key string has to match. Now, as I've been talking, we see a dead timer expired on 10.10.10.60. That's the Kali PC running Loki that is the rogue router, right? So let's go back to the Kali PC. Now, using KEY as a key is a bad idea, as we've established. It should be pseudo-random. It should be, a mixture of uppercase, lowercase numbers, and symbols, not in the dictionary. And we're going to see how easy it is for Loki to crack this authentication key and then reestablish a peer relationship with the routers. So at this point, go back behind this window. We can see there's some confusion going on with Loki, got new peer, sending hellos. It's kind of confused because the OSPF configuration has changed. So let's restart Loki, loki.py. Make sure that we go to the gear icon using Ethernet 0, OK. We want to go to routing, OSPF. Now notice that we're displaying our two routers, 10.1 and 10.2. But notice in the auth column, it says crypt as opposed to none. Well, let's go down to the cracking tab, and we'll use brute force. We'll choose the 10.10.10.1 router, and we'll crack PW. We could also load up a word list. We don't need it, though, but look how quickly we see key. It was almost instantaneous. If it's a stronger key, we could load up a word list down there and go at it. So we want pseudo-random, long, strong keys. And they should change every 45 to 90 days. Now let's peer. Click on hello. Go to connection, area 0. The type is authcrypt. Type in the KEY here. And the key ID is 1. Do the hello button. So there we go, two-way. Going through the states, X start, loading. Now, Loki is not very reliable. It's buggy, so it's still showing loading. But the truth of the matter is if you went over to router 1 and router 2 and you issued show IP OSPF neighbors, you would see this Kali PC at 10.60 as a neighbor in the full state. We've seen how we can easily crack weak keys, especially MD5 keys. And as an attacker, we can use these and really brutalize a network in many different ways, undermining the entire control plane and data plane. Now, realize that the weakness that we just exploited was not the weakness of MD5, actually. It was using a weak key with MD5. Now, should we use MD5? No, it's got a published vulnerability, and it's been cracked in a very specialized way. It was actually a weak certificate server using a really weak key and a bunch of daisy-chained PlayStations. So that's one of the main published cracks, and we should avoid MD5 in these situations. So with an HMAC, you really want to use something in the SHA-2 family and a long, strong pseudo-random key. Now, as of this moment, Loki doesn't support the cracking of SHA-256 authentication yet. Let's go back to router 1. Let's modify a key 1. So global configuration mode. We'll go back to the keychain, OSPF-keys. And we're going to modify key 1. And let's do a different key string. The key string, capital Cisco 123 exclamation point. A little bit stronger. You've got symbols, numbers, upper and lower case. So it is substantially stronger than KEY. Now let's go ahead and got to spell this correctly. Cryptographic algorithm. Let's go ahead and use HMAC SHA-256, which is really a best practice, at least. Now notice that, again, they're not compatible. Router 1 and router 2 and the Kali PC don't have compatible keys, so our neighbors are going down, quickly failing. Let's go to router 2 and modify those keys so these two routers can peer with each other and authenticate. So on router 2, we'll do key chain router dash keys, remember, different name, still key 1. And now our key dash string is going to be capital Cisco 123 exclamation point. Again, the crypto algorithm is HMAC SHA-256. We should start seeing some neighborship coming up. There we go. Loading to full, loading done for process 100. 10.10.10.1 on gigabit 01. However, if we keep waiting, we'll start to see the neighbor relationship with the Kali PC going down, okay, broken. Let's do a show IP OSPF interface, not neighbor, but interface gigabit 01. Look at the bottom down here. It says cryptographic authentication enabled. Sitting this SA, Security Association, key 1, there's our algorithm, and the key chain router dash keys. Let's look now at some network-enabled services and devices. First of all, we have System on a Chip, or SoC or SOC. This is basically driven by miniaturization and commoditization. Think about your smartphone, for example. We forget sometimes that your iPhone and your Android and your pad, your tablet, they're actually computers. They do a lot of the same things that your desktop workstation and your laptop does. But they don't have the same kind of space as your desktop or even your laptop. And that's where SoC comes in. It provides a CPU, a graphic processing unit, a North Bridge component that handles communications between the CPU and other components, a South Bridge, which is a second chipset, and often cellular radios and other radios, for example, Wi-Fi radios. And there's a bunch of architectures out there like GeForce, Adreno, ARM Mali, and PowerVR, different varieties that are now network enabled, ready for IoT or IoE, Internet of Everything. We also have RTOS, real-time operating systems. Most operating systems do multitasking, but the scheduler, let's say in your Windows 10 machine, tries to make sure that your computer is handling multiple threads and remaining responsive to that end user. It has a scheduler. Well, in a real-time operating system, the scheduler is going to give a predictable or deterministic execution pattern. So this is going to be found in embedded machines and embedded systems that have real-time requirements. Often, it's going to run on what we call microcontroller applications, a small resource-constrained processor that is typically found on a single chip, like an SoC. And we're finding these in IoT devices. There's also HVAC controllers. Obviously, you can control your HVAC as I can right here in my home. It's able to connect to my Wi-Fi router, and I can have a web page where I can actually configure timing settings. If I'm out of town, I can actually remotely access this and control my HVAC at home. This is a huge system in facilities and large buildings and large enterprises, often falling under the auspices of the facilities management, but because it has security vulnerabilities, if connected to the internet for remote access and remote control, as a security practitioner, your team or your security operations center needs to be involved in the HVAC controller initiative. There's also building and home automation systems, remotely opening your garage, for example. These are integrated systems that are tied through Ethernet throughout your entire home and then can connect to the public internet through a Wi-Fi connection, or maybe your cable system or a satellite system. Or maybe you're going through a third-party provider. So you can use your iPhone or your Android and manage pretty much all the systems that are internet connected throughout your home. In other words, you've got a smart home. IP video is very popular. This can be used for security systems. It can be used for monitoring babysitters, for example, or monitoring when services come into your home. Maybe you have a private chef, people doing pest control, your pool person. So internal and external IP video for the home, and of course, closed circuit television and IP video throughout the corporate enterprise for a wide variety of reasons. There's a wide variety of sensors, IDS and IPS sensors, but also motion sensors using a wide variety of different technologies like microwave or sound. There's physical access control systems, audio-visual systems that go beyond just your IP phone or IP video. Scientific and industrial equipment is network enabled more often than not. The best case scenario is that it's air-gapped from the internet, but often that industrial equipment cannot be air-gapped for reasons of interoperability with other partners or government contracts or storing information on the cloud. Some of the security concerns of SoC and RTOS is that it's, poor security. Often they use older operating systems, or it's an open source operating system that's not hardened or locked down. You have the lack of regular updates on these types of embedded systems. Also, there's privacy issues because so many of these devices are commoditized and exposed to the internet. We're finding more and more malware threats because of the older operating systems or less hardened operating systems. And a lot of these systems don't use trusted computing, so it's easier for hackers to get root access to a device that's running SoC or RTOS. Some of the RTOS security concerns are code injection, privacy issues, exploiting shared memory in the RTOS, and process and thread priorities being leveraged for a hacker's malware or scripting. There's also denial of service attacks towards RTOS systems as well. We're finding vulnerabilities in inter-process communications on the real-time operating systems. Some of the automated systems that we mentioned earlier, alarm systems, camera systems on the inside and outside. Don't forget about sprinklers and irrigation systems. Those are being network enabled. Obviously, inside and outside lighting has been automated and enabled for a long time. That can be managed through your web portals remotely. Various IoT appliances. Refrigerators, of course, are becoming more internet enabled and remotely controlled. Some of the challenges with IP video and webcams is just the overall lack of security in the operating system, using weak passwords for access, poorly coded software, malware, specifically for webcams, and we've seen quite a few threats that have shown up where people who have had their webcams accessed either on their laptop or on their PCs, part of a botnet all over the world. Privacy issues are also key, and so if you're in a compliance environment, HIPAA or Sarbanes-Oxley, you have to be concerned about exposure of IP video and webcams on the internet or Instagram or other social media sites. You have to lock down your mobile access and possibly use TLS for management. Where are those recordings being stored? That's a key issue for privacy and security. And, as we know, they're often used for spying or spyware. There's also supervisory control and data acquisition systems, or SCADA. This is a subset of the ICS, the industrial control systems that are used by a wide variety of utilities, for example. As a security practitioner, you need to understand your organization or your customers' control and management system architecture. These could be water systems, electric power companies on the grid, traffic signals in a metropolitan area, mass transit systems use SCADA systems, environmental controls, and manufacturing systems. A lot of these systems are not air-gapped and are actually on the internet for remote access, remote control, and monitoring purposes. Some of the main security concerns to be aware of on the exam for SCADA are cyber terrorism or cyber warfare targets against the power grid or water systems. Typically, they weren't designed with security in mind, so more often than not, they have poor security, not just in the design, but also in the operation and deployment. And remember, just like the nuclear reactors in Iran, they thought they were air-gapped, they were still able to get the Stuxnet worm/virus/remote access Trojan onto their systems by an individual coming in and putting their laptop on the internal corporate network. So physical security is tantamount. There's often a flawed authentication process between the devices or a complete lack of authentication for endpoint users. There's weaknesses in security protocols that are proprietary, as well as the services and applications. Internet connectivity, sometimes without the knowledge of the actual system operators.